Uh, Hi all. So in this session, we'll be seeing about clock domain crossing. This is like one of the important aspects in VLSI, right? Especially for the front end designers. Where exactly this clock domain crossing comes into picture is like a designer kind of, has multiple blocks, right? And it could work on multiple clock domains, and there could be potential crossings of a signal or port from one clock domain to another clock domain, mainly with respect to when it's crossing from one block to another block, or even within a particular block, we might have multiple clocks, right, which are coming into that block actually. Yeah. So basically, they right. So this is a clock we have, and let's say the path, right? So this is the path. So in case we have the same clock which is going to the both the flops, right? So usually this is like the launch flop and this is the capture flop. So there might be, you can have like one clock here. So in this case, there is a synchronous design here, because we both the flops are getting the clock at the same time, and basically all the timing checks for this is taken care by the synth initially, and later on it is taken care by STA as per at the later end of the VLSI flow. So this is for the synchronous clocks. So that could also be the case where we have different clocks to both the flops here. So this is the data that is coming here and going here. So this is the data, and this is the Q pin. So this might have clock A here, and this might have clock B here. So in this case, both these clocks are asynchronous in nature. So in that case, basically, when we say asynchronous, no, they're like out of phase to each other. One is like they're out of phase. All right. So this is clock key, let us say, and the other clock is kind of little bit shifted. And so here, this case, these two clocks are like, you can see that these two clocks are actually out of phase here. And also, so in this case, whatever the setup time and hold time checking using the synth and STA, that is not applicable, because we don't really know when this particular edge is going to come with respect to the launch flop. So it does not have a predictable behavior here. So you'll not be able to do this using the setup and hold checks, which you usually do during for the synchronous paths, right? So in this case, problem is in case the data changes during this window, right? So again, the same metastability issue will come here. So the data it toggles in between this window, it will lead to the metastability. So when it leads to the metastability, what happens is whatever the combo logic, the functionality of the combo logic could go wrong, and all the values which are propagated and fanned out will be completely wrong, and it will just cause complete hang down of the chip actually, and it will cause millions of loss to the company here. So that is the issue with respect to the when we have asynchronous clocks, and there's a signal is crossing from the clock A to clock B, or the asynchronous clocks, right? This will lead to the metastability here. So it will actually go into an unknown state here, right? It will just go into an unknown state here. you really don't know what is the state, and so it could be either 0 or 1. It is the in between state here, and it could settle to any of these values, and it gives an uncertainty behavior for us. So to solve this, basic kind of solution is to go for a two-flop synchronizer. So what a two-flop synchronizer will do is, like, it will delay the signal to the it will be based on the destination clock. It will delay the input signal by 2 clock cycles. So this is a two-flop synchronizer, and there's a capture flop. There's a launch flop. So this is on clock key here. So all this is on clock B. The destination flop as well as the synchronizer all are on the clock B domain. So these two flops form the synchronizer here. So the first solution that we're seeing here is the synchronizer here. So these are two flops. What does it does is, so whatever the input signal which gets captured at this stage, instead it gets captured at this flop actually, instead of this flop. So again, the same thing would happen. We would get this kind of a metastable state, but at the very next stage, right? So the possibility is that it might may or may not settle down. So let us, and by the end of the next flop, it will get settled down and it will come to either 0 or 1, and then it goes to the capture flop. So this is how it's synchronizer solves the problem. So at this point, right, it will again cause the same thing, metastability issue. While coming out of this flop, the data will be again in that metastable state. But with giving these 2 cycles delay for the particular signal, so once it comes out of the synchronizer, it will either come settle down to 0 or 1, and eventually go to the capture flow. So we do not have the issue of this metastable signal, and the functionality works. So the metastability again is dependent on multiple factors based on which we decide the number of flops. So it could basically, most of the designs have like 2 flops in the industry, but that might be cases where it can be 3, or based on the mean time between. There's another factor called the mean time between failures. So based on that, we decide the number of flops for the synchronizer. Yeah, so this is a basic intro about the clock domain crossing. So we'll stop the discussion here. Please do let us know any questions or any queries on this basic introduction about clock domain crossing. Thank you.